And so I've tried to put in the notes like a lot of the links and the content that I've developed over the years. So these would be the Google Doc notes. And I've just put a lot of link to the PowerPoints here. Then I started in on gain bandwidth and open loop gain. All right, with an example, but everything you need to know should be in here and the previous videos. And just to let you know, I might have to step away for a second. Contractors coming, they should have been here, but they're not. And since everybody in the house is wearing noise canceling headphones, I might be the only one to hear them. All right. So we touched a little bit upon things last time where we have gain bandwidth where V out over V in of an op amp equals 1 or 0 dB. Now, the way I've done it like this, that kind of assumes I've got the negative terminal tied to ground, and that would be in, and that would be out, right? And then the other thing is the open loop gain, which you're somewhat familiar with from 98, because that's the thing that we always set goes towards infinity. All right. And so if we look at a data sheet, okay, zoom in a little bit. We can see the gain bandwidth product, note 5 tells you the conditions. And then these are giving it to you in megahertz. Now, just something to know, it says typical 0.8.
Tôi coi rộng chứ.
All right, I'm just going to mute everybody, okay? But if you have to ask a question, of course you can. So this is typical, but this is minimum. And so that's the actual guaranteed value that you can count on when you purchase this part. So if your design isn't working due to the gain bandwidth only being 0.5 megahertz, you're a bit out of luck, right? Even though typically you'll get 800 kilohertz, that's all their guarantee. All right. So let's just pick like 800 kilohertz. All right. And then open loop gain, large signal voltage gain for a load, minimum load of 2 kilo ohms, which we've talked about. And the power supplies are a minimum value. We're getting between 700 and 300 volt per millivolt. All right. So that's basically, again, the same thing. They're only guaranteeing the 300, even though typically you should see 700. All right. So That's the LT101, and the gain bandwidth equaled 300 kilohertz, right? And right. So now that we know these two things, right, we can determine when and where things are going to work for us. All right. And let's just put this, it's a rough eyeball, and we'll call that 300 kilohertz, right? And we'll call that 0 dB. All right. So that point, right, is where the gain V out equals V in, and it's just gain bandwidth. All right. So now all I have to do is draw a line from there. Okay. And we can call each one of these steps 20 dB. And I'm going to try to that's about right. Okay. And so we get 109 dB. That's probably easier to just round it up to 110, but let's just scale it in here or draw it in. So 20, 40, 60, 80, 100, 120, 140. That's 110 dB. All right. And that would be if it were constant, right? And so then the whole model becomes that. And once we have that, there's just a simple equation, is that the magnitude of whatever your design is, high pass, low pass, band pass, notch pass, just not inverting, inverting gain, whatever that is, right, has to be less than the magnitude of whatever the op amp is. And it has to be like 100 times less, right, to really make sure that it's acting ideally. So here's the thing. That means that this, so that's 110. We can come down here, right? That means, anywhere below this line, this design space will work. All right. But a lot of times we just use these lines here as our limit, and we know that it'll be somewhat less. All right. And it's a little bit better than 100. times less. But whatever's going on here, as long as it's less than this, it's not a problem. All right. So for instance, if I have h of s equals 1 over s, right, which is 0 dB here, right, at 1. These lines are parallel, but eventually it'll stop working when 1 over omega is greater than this, the open loop gain. All right. So in this case, the limitation is really at low frequencies, and it's the open loop gain just isn't infinite. All right. This will still work as an integrator though, by the way. All right. But that frequency range will work here. Now, what about h of s equals ss plus 10? All right, well, that's a high pass and it has a break frequency here at 10. And in fact, it's going like this, and it'll work right till where it hits here. Now, what if it was times 100, right? That would be 40 dB. Make that a little darker. So the break point is still 100, but it's going to even out at 40 dB. All right, that's 20 dB per decade. And so this will work like a high pass filter until this point. All right. Now, if that's not good enough, right, you have to buy an op amp that pushes this line outwards, right? And that's getting a smidge messy. All right. I'm just going to redraw that. Oops.
Professor, can you explain again how do you get this Foley plot?
I'll go over it briefly, right? But this was from last time, right? And so this right here is from the data sheet, and it's the DC value, and you just draw a straight line asymptotically here. And then that point is 0 dB, and it assumes like a first order integrator type thing. So it's 20. So I just take around 300K. Oh, sorry. It's in the wrong spot. And that was 20, 40, 60. So that's about 110. And it goes here. All right. So really, you're given this value and you're given this. where, right, normally you would be given some number, we'll just say A, S plus B, where that's the break frequency. No, you're given this point here, not this point here. So you just draw them asymptotically towards each other. And you can back calculate what B was. Yeah, so should you use the minimum values from the data sheet? Yeah, if you want it to work every time, but there could be times where you might be allowed to use the typical values, and the LT spice will use the typical values, actually. All right. And the thing is, though, is this really, you probably want to use the minimum values, because I was doing a pulse width modulated DAC and trying to make the highest frequency one, and it wasn't working. And I looked in LT spice, it's working there, but it's not working in real life, like no matter what I did. And it took a lot of debugging, but in the end, I realized that the gain bandwidth wasn't what it said in LT spice. And you look up the data sheet, and yeah, it was more towards the minimum. And so that's why it's kind of important. Okay. But here's the thing. If you're doing your homework or checking your work or doing your project, you can just use the values in LT spice, and that's fine. All right. So anyway, your design space can be here. And what I was going to, the next example was going to be, what if I had 10 S plus 10 times 10, right? Well, that's a low pass filter with a gain at 20 dB, right? And that'll work, right? And so in fact, according to this idealized model, it works for all frequencies, right? But sometimes what happens is, what if you were doing 1 meg, S plus 1 meg, right? And then we'll say times 10. So the break frequency is a megahertz. All right. So we still have our 20 dB gain. So let's do that Bodhi plot. There's our megahertz. And then there's our slope. Well, in fact, what will really happen is that it'll work. All these frequencies, it works. And then you'll see a low pass filter with a wildly different gain, right? And you might say, well, wait a second, that should be 1 over RC times S plus 1 over RC, which, yeah, your resistor can maybe vary 10%, and the capacitance can vary 10%. And you can calculate that, how much that break frequency will move around based on RNC. But this is so far off that it's not due to your resistor capacitor variances. All right. It's the op amp. And what had happened to me is that I was really getting like this. So this might have been LT spice. No, I didn't actually design, I designed it for here, but the whole line was lower than my thing. even though I thought I was in the right regime, oops, this had shifted so far to the left. All right. So that's basically graphically kind of telling you what's going on. All right. Now, we'll take this a little bit further. Same example. Okay. Now, what if we just had a non-inverting amplifier? All right, we have this, right? And if the open loop gain is infinite and we derive all of this, right? Out over n equals 1 plus R2 over R1, right? Now, what if that equaled, 1, 10, 100, and 1,000? What would that look like? Well, a gain of 1, regardless of R1 and R2, right? If the gain is 1, which happens to be a buffer, right? R2 is 0 and R1 is infinite. We have 0 dB, right? And it goes right out to here. And it stops working. If we have a gain of 10, that's 20 dB. And it stops working. A gain of 100. Right? And so on, right? So the frequency range of where it's valid keeps getting smaller and smaller until, in fact, you can't do it at all, right? So that's, graphically what's going on is that, you have your transfer function that you want, right? Which just happened to equal gain. And that gain has to be less than the, that transfer function of the op amp, right? So let's hop back to the notes, right? That's all I said. I just said the same thing here. I've used the magnitude. And then there's some models that are used, all right? And one is there's a finite open loop gain. Now, or a constant, it doesn't vary with frequency. Now, it might be infinite or it might be infinite, right? But there's no frequency dependence, right? So that model is just constant. Now it could be infinite, but it's still, there's no frequency dependence. All right. The next one is the integrator, right? And now this one I'm just kind of drawing randomly, right? There's not a necessarily a data sheet associated with that. And that's AV over S. All right. And so, you know, something over S looks like an integrator. So that's just why I call it the integrator model, right? Then there's what I would call the first order low pass, where you have some open loop gain, S plus omega naught. Now, what I'm going to do is sneak an omega naught in here so that no matter what omega naught I choose, if I've chosen the same open loop gain here and here, this will line up, right? Now this could overlap this perfectly, but it doesn't have to, right? And then there's another one we deal with. We have our open loop gain, and I'm just going to put in 2 omegas there. And it's a second order. All right. And color scheme I didn't quite like, but where you can have, you know, a breakpoint and then a breakpoint like that. All right. But in general, right, up to this point, either if I break here or I have this, usually this point here is beyond the gain bandwidth, or you hope it is, right? It's not always, but that's kind of the assumption that I make, right? So those are the models that we have. And then to have any kind of you know, if I want to know what is, where is this circuit going to work? Right. Well, I know this is minus 1 over RCS, right? I take the magnitude, the minus sign doesn't really matter. I just have to make sure that I'm below whatever model that I've drawn. Okay. Then that's where it works. So if I happen to choose this minus 1 over RCS, right? It's going to stop working here, and it's going to stop working here. So that would be the frequency range, right? If it wasn't compared to this green line, right, the way I've drawn it, well, it's always below, it's in parallel, so it always works, right? And now let's just compare to this yellow line. Well, this is in parallel, it's always working, and it stops working at low frequencies. Now, there was really nothing special about the way I drew these, that the second order one is always to the right of the integrator, which is always to the right of the low pass. I just drew it that way so one could see it. All right. And the thing is to solve for this one mathematically is quite involved. I've done it in the notes, but really, if you see this on the exam or even the homework, you know, where does this work? You really just want to draw it out on a Bodie plot and just say where it works. Okay. And I'll be very specific. I'll say something like, do this graphically, do this mathematically, do it graphically and mathematically. All right. So I'm pretty clear. All right. Now that's the graphic way. All right. But let's, you know, why does this work mathematically? Right. Because if we have a mathematical equation, we can automate it. We can, you know, much more rapidly come up with a solution. All right. All right, if you recall, I can replace this with a summer, right? There's a transfer function inside. And that's out. Now, when we, in our signal flow diagram, we usually just have a constant there before we feed it back in. And we're going to just call that beta, right? And then the input is the input. Now, what is beta? Well, if you assume that I minus equals I plus equals 0, because Rn is infinite, right? Then really this spot here is just the voltage division, Vx, right? So but V out is the supply. So it's R1 plus R2. And since that's the voltage, if V out is being scaled by some value, right? And V minus equals Vx times V out, then beta is really just that voltage division equation. So now let's, now that we put it into our system feedback form, right? V out equals, here's N times HS. Okay. And I'm just going to write op for op amp, because there's a transfer function of the whole system that we want, right? Then we have V out times beta. Oh, it's subtracted. Times the transfer function of the op amp. So we collect our V outs. right? And then we solve for the transfer function of the whole system. Right. And so we're going to use that quite a bit. Oh, excuse me. The beta is there. Now, let's put in a model. So what if we have HFs of the op amp equals open loop gain? All right. And a lot of sometimes I've seen AV, and you might see me use them interchangeably, but I'm trying to keep a handle on that, but it's the open loop gain. So what if that's what it is? All right. So V out over V in equals the open loop gain 1 plus beta, the open loop gain. Now you might have gotten to this point in your circuits class, but through a different way. And you would then say, let open loop gain go to infinity, right? And then you get 1 over beta, right? And then you get the equation. But really, what's going on is that we want beta open loop gain to be much, much greater than 1 in this case, right? So if that's true, we get right? And then the open loop gains cancel. I have 1 over beta, which is 1 over R1 plus R2, which ultimately gives us R1 plus our non-inverting gain. All right. So here is the relationship, right, that tells us what has to occur to make this appear as if it were ideal. All right. And so what's our maximum gain? Well, if beta open loop gain has got to be much greater than 1, then it's got to be much greater than 1 over beta, which would equal 1 plus R2 R1, which is in fact the gain we were talking about. So if this were that open loop, if this were the HS of an op amp, right? Actually, so in this case, the open loop gain is just a constant, right? And R1 this, right? Whatever that is, just has to be less than that. Okay. That's it. Now, what if we, but what if HS of the op amp were the integrator. All right. Well, I'm going to go back and just rather than rederive it, V out over V in equals HS of the op amp 1 plus beta times H of S of the op amp. And so I get AV divided by S 1 plus beta AV divided by S, multiply through by S. Okay, and now what we need to happen, right? This has to be bigger than this, but this is what? J omega. So we have to kind of, the magnitude of J omega has to be less than beta open loop gain. And so now before, right, it didn't matter what the frequency was, right? You just had to be less than that. Now there's a frequency dependence to it, right? And really that's, the frequency has to be a lot less than beta here. Because if this is bigger than that, the open loop gains cancel out. It's 1 over beta, which gives us our ideal gain. And here's the thing, beta is inversely proportional to the gain. So if you have a high gain, beta is small, and that means, omega has to be small, right? So if beta equals 1, right, because the gain is 1, we can get a much larger frequency than if the gain equals 10, beta equals 0.1, 0.1 times open loop, we've lost a decade. So omega has to be a decade smaller, right? So this is AV divided by S, right? And so you can see that I can have a smaller gain and a much larger frequency range. And if I have a higher gain, right, that frequency range where it'll be ideal is reduced. And so, yeah, in your circuits classes, we always made sure that you were operating well away from this line so that it didn't really involve, you wouldn't really see the effect. And even though the oscilloscopes, we have really good ones, it can be quite difficult to measure at a megahertz, not because the equipment is bad, but you won't see, basically this capacitor has a resistor and an inductor along with it. And so you get, the measurement is true, but it doesn't look like the theory. All right. And so that's why we use, the frequencies that we use. All right. Now, yeah, if we had HS of the op amp equals right? This is a overdamped system because there's two, break frequencies. They're both real and different, right? So essentially it's overdamped. All right. And again, I can put this back into that equation, right? Now, yeah, it's going to be open loop gain, omega 1, omega 2, right? I know this is going to multiply through by 1. Right? And then it's going to cancel it's going to cancel the denominator. So I'm going to be left with beta open loop gain of that, right? And now, yeah, it's a little more complicated, but yeah, the magnitude of these things, right, has to be less than that. All right. Now, the other issue that now we're about to talk about is we have the op amp can turn into a second order underdamped system. All right. Even though you start off with a op amp that's clearly second order overdamped. All right. So let's just now, the only reason why I'm doing it like this is so that I can specify this number here can be will match all the other models. All right. But really, this whole thing would be the DC one and the open loop gain from the data sheet. All right. But in the homework, you might see AV times some number, or you might see a number. And that's really just me keeping track that at 0 hertz, well, yeah, at 0 hertz, these cancel out and you're left with that. So yeah, it's basically, so it will give me the data sheet number. Anyway, let's do this. So V out equals V in, so beta equals 1, right? And so I'm just going to do it out again. So V out will equal V in HS op amp minus V out HS op amp, right? excuse me. Hello? I really apologize for that. I had to take that. That was the contractor. So anyway, V out over V in will equal that HS of the op amp 1 plus, now there's no beta or beta equals 1, HS of the op amp. All right. All right. Now, since this is second order, let's just put it into some kind of a second order type form. All right, where so the thing is right, if zeta is 1, you have 2 repeated poles that are the same. If it's greater than 1, you have 2 distinct poles, and so it's underdamped. And if it's overdamped, and so if zeta is less than 1, you have a pair of complex poles, and so it's underdamped. So I think we agree that we can see that there's, in this form, right, there's 2 distinct real poles. And so the op amp without a feedback network is underdamped. But now let's just multiply everything out, right? I have the open loop gain, omega 1, omega 2. I have S squared plus omega 1 plus omega 2 S plus omega 1 omega 2 plus open loop gain omega 1 omega 2. Right? So think about it. If we're going to find over, under, and critically damped, all we need to do is look at the denominator, right? And what the quadratic equation is minus b right? That'll give us the 2 where the denominator is 0, right? And so just looking at it, b equals omega 1 plus omega 2. But now C equals omega 1, omega 2 plus open loop gain omega 1, omega 2. All right. And before, C was just this value, but now we've added something to it. And to know if the system has changed to underdamped, right? If 4AC is greater than B squared, right? These roots will be complex and it'll be underdamped. If it's equal, it'll be critically damped. And if it's less than, overdamped. Now, why is this important? Well, this is a step response, right? We have a step input. Right? And, you know, we know that there are capacitors and resistors in here, that it could be a second order system, at least a second order system, which it's, and we can just draw a few things. Like if it's underdamped, it'll look like that. I mean, that's over, right? Under will go a little bit faster, but the curves are actually hard to tell, actually. But right. So in fact, you can put in a step, right? And even if I have +5 and -5, right? If my step is 5 volts, right? My output can go above the power supply just because it stores enough energy to do that. It's turning into an oscillator, right? And so you want to know, if you hook up your circuit and you're seeing this weird thing here, well, it could be your overdamped system has turned underdamped, and now you're getting oscillations or ringing for that. All right. So if we look at homework 8, which is new, by the way, right? I have a link to previous solutions. Here's a Bodie plot. It's from LT Spice. So you can start to see the phase drop. So it's at least a second order, right? Because it goes down to -90, and then it's starting to go down again. But just indicate where the open loop gain and the gain bandwidth points are on that. And then here, right, just answer these questions. Where does it look infinite, right? Where does it look finite but constant? You know, what range from here to here, from here to here, right? What frequency range does the op amp behave like a single pole low pass filter? What frequency range does it look like an integrator, right? So right, if something is finite and has no frequency response, it's flat. So wherever it's flat, right? If something is acting like an ideal integrator, right? a line with a minus 20 dB per decade slope, right? And if it's acting like some kind of low pass filter, first order would be here. If you see another break, well, it's no longer acting like a first order filter, right? What I'm trying to say is between here and here, it's acting like a first order. Then when you see that other break, oh, now it's acting like a second order. Because if I guess what I'm saying is if I zoomed in and only showed you 1 millihertz to 1 kilohertz, you'd have no idea that this was happening, right? It would look like a first order to you, all right? Then here, right, you can do this graphically, but here is a non-inverting. And what are the frequency ranges for which it works for these various gains, right? Here is, you have these various models, finite, integrator, low pass, right? And you have an inverting integrator. And I've already kind of showed you how to go about that. While it is possible to do this mathematically, it'll take you too long. And then here is another thing where does it work, right? The key to this is that this is a non-inverting amplifier with a gain of 1. So where this stops being a gain of 1, this won't act like a low pass filter, a high pass filter, right? Then here is another op-amp model. When I hook it up in this configuration, will it be over, under, or critically damped? And then here, where does this filter stop behaving like an ideal high pass filter? You just identify and explain it. And then here, same thing, it's another high pass filter, and you just identify and explain where and why it stops working. All right. So on the midterm, you will get questions like that, or a subset of those questions, right? But pretty much this is 8 and 7 are kind of the same type of question, but you could get a question like 6, 5 and 4 are similar questions. It's just different circuits, right? You could get a question like 3, and 2 is built into every question, right? And you can't understand anything unless you can define what the gain bandwidth and the open loop gain is. So that is, I forget what order, but yeah, there's going to be a question on DF2, and there'll be a question on gain bandwidth. And then coming up on Wednesday, we'll have a question on the Fourier transform coefficients. Although really we've been using the Fourier transform where S equals J omega every time we do a Bode plot. Okay. Any questions? Yeah, you know what I have to do? I have to make sure that the midterms don't collide. But yeah, we're on track. We're totally on track to take the midterm. Now, no, there's actually 5 questions. So there's something that where we model a mass, spring, and a damper as an RLC circuit. All right. Now, yeah, I mean, this is a whole other thing, but if you have a damper and a spring kind of attached to an elevator, and then you have a mass, right? You have the velocity of the elevator, the velocity of the mass. I can actually turn this into a voltage, which represents velocity. The spring represents an inductor. The damper is a resistor. And then the mass actually is a capacitor. Instead of velocity, we measure voltage, right? And so now we can do our Bode plots, our things over, under, critically damped. What is the step response going to look like? Things like that. And then the other one is control. And just to give you a brief idea of that is, so far, right, we've had numerators, and now, yeah, we've had real and different, the same, and we've talked about a pair of complex. But the thing is everything, right, we've had is to the left of j omega. Because when you take the inverse Laplace transform, you get things that are proportional to exponential decay. All right. So if I had A and B, I'd be like this. If they were repeated, they'd be like this. And if they were imaginary, it would be like this. But still, everything is here. We're going to talk about is what happens when, and so essentially, if I put in an impulse response, no matter what, it's going to stabilize to some value, right? A low pass is going to stabilize at a DC. A high pass, is going to stabilize at 0. A band pass will stable at 0, and a notch will stabilize at a DC, but it stops. But when we start getting poles at 0 and here, we can get oscillators, things that integrate, and things that exponentially increase. And those systems are out of control. And so sometimes you have some kind of robotic system that basically you put in a step impulse and it falls over. You don't want it to do that. And so you use control theory to make that not happen. And that would be the 5th topic. So Fook, what is the purpose of the cutoff frequency or center frequency in the DF2 problem? Which problem? Which DF2 problem? All in homework 7. All right, homework 7. Okay. So I'm gonna, I think I know what you're talking about. And so if, so we've talked about really repeated roots and, just first order. And so in this case, right, this is omega naught for, and a low pass would have omega naught S plus omega naught. And really, it's 3 dB down, and the phase is minus 45 degrees. All right. Now, if I just start squaring this, right? Yeah, this slope goes that way, but these 3 dB points, it goes down 6, it goes down 9, and so on and so on. The Butterworth filter keeps this frequency, the bandwidth here at 3 dB, right? And the slope gets, a fourth order will have minus 20 times 4 slope, right? But this value, this omega naught, if you will, is no longer the break frequency. It's near it, right? But you wouldn't see it. All right. And a second order, right? Omega naught, it's really, all right, this is no longer the break frequency. All right, because it could be over under critically damped. Omega naught actually is just where in this second order system is where the phase is minus 90. All right, but the bandwidth is just where is that minus 3 dB point. All right, because it's a Butterworth filter, you just say that. And so I'm just telling you the bandwidth is such and such, right? To tell you that, yeah, if you wanted to, well, that's the solution. So if I say fourth order low pass filter with a cutoff frequency of 200 kilohertz, right? That's just where that 3 dB point is. You don't really actually have to worry about it. These are just the numbers, right? To make that happen, right? So here, when you run, you give it a frequency, in this case, 44 kilohertz, you tell it third order, and you just say, that's where I want that 3 dB point to be. It's going to be a Butterworth, and it's going to be a third order. And then when you run it, it'll give you the constants, and then it'll give you the magnitude of the Bodie plot. All right. But it's that point right there becomes 43 kilohertz, because that was the specification. And then this slope, because it's fourth order, would be 4 times 20. Okay. So you don't really need to know that, I think, but it helps. Right. You're right. You don't use it in the calculations. Now, for that program, the notch filter, and I'll just run this again. You don't give one frequency, you give two frequencies, and then the notch is in the middle. All right. But that's just where we're headed. But, you know, to kind of maybe try to summarize it, what we're going to do, like again and again, is we have a new transfer function. We call it Q of S. And then we're going to have some kind of transfer function going on, and it could be an op amp. It could be a robot, right? A motor, heating system, right? And then we're going to put it in a negative feedback, right? And there's going to be some kind of transfer function for the feedback, right? Today, that transfer function of the feedback was just beta. So here's the thing, right? We have a summer. We have H of S. We have V out, G of S, and we're subtracting that, right? That's in. And so this could be the dial on the heating system, the furnace, the motor, the steering wheel, where you want the robot to go, right? And then without this feedback network, you could have something that's out of control, right? Something that's E to the T, right, is something that it's going to explode on you, right? So we add this, but the trick is, what do we add to make sure that we bring it in control? All right. And then, yeah, the part right now, right, for a rectangle, we kind of use UT minus 1, but we don't repeat it. Things that repeat forever, we use the Fourier expansion, right? And so that's a little more signals, all right? But this kind of business, right, it's the op amp, it's the controls. All right, so it's not a, now we're going to get, I guess you could say we're getting into more applications, right, of this control theory. Anyway, I know you guys got to go. Take care.